This is a naive Bayes model part 2 in machine learning, and let's go ahead and get started. So the questions I'm going to be answering in this video are going to be two general questions, and each of those general questions is going to be broken up into three sub-questions. So the first general question is, what is the naive Bayes model through a specific example? Right, and the three sub-questions I'm going to be answering to answer that question are, what is a specific scenario where we can use our naive Bayes model, and what is the data set for this specific scenario, and what is the class of a specific example using the naive Bayes model. Right, so those are the three sub-questions. Now, the second general question is, what happens when a feature is not present in the data set for a naive Bayes model? Right, and I'm answering that through these three sub-questions. What error occurs with the naive Bayes model when a feature is not present in the data set? How do we fix the error from the feature not being present in the data set? And how does the error get fixed for a specific example using the naive Bayes model? All right, and that's what I'm going to be going over in this video, and let's move on. All right, so an example where the naive Bayes model is used. So this is going to be a concrete example where we can use the naive Bayes model to solve a problem. So say we receive a package of wood every day, and the package can be dented, it can be discolored, and it can be opened in some way. And these are our features for the package, right? So X represents a package, and it has three features for it. It has the dented feature, it has the discolored feature, and it has the open feature. Right, so whenever you see an X, that means that's a package, and it's going to have three features. The dented feature can be three values. It can either be none, which means it has basically no dents in the package whatsoever. It can be mild, where there's a mild amount of dents in the package, and it can be full, where the package is basically fully dented. The discolor feature can also be none, mild, or full. So when the discolor is none, that means the package has no discoloring in its paper whatsoever. And when the discolor is mild, that means that the package has a mild discoloring to it. And when the discolor is full, that means there's a full discoloring to it. The package is kind of faded away. And the open feature can also be none, mild, and full. And when opened is equal to none, that means that the package is not opened at all. It's fully sealed. When open is equal to mild, that means that the package is partially open. And when open is equal to full, that means that the package is fully open. Now, the package can either have wood that is intact, that is like fully intact wood, or the package can have wood that is broken within it. And these are our two classes, right? So our package can either have intact wood or can have broken wood, right? And so our set of classes Y is equal to intact and broken. And this should answer question 3.1. All right, let's move on. All right, so the data set for our scenario. All right, so we want to know if the wood will be broken before it is delivered to us, right? Because if it's broken, we want to send it back. So we can get an image of the box before it has arrived and use it to measure the dents and the discolor and the openness of the box or the package to predict the probability of the wood being broken or intact, right? So say we record the shipment of our packages over 5 days and get 5 examples for our data set. So here we're in example 1, we got a package delivered to us that had a mild amount of dents, it had no discolor, and it had no openings, and we found that the wood inside the package was intact, right? And for example 2, we found a box that had a mild amount of dents, it had mild discoloring to it, and it was fully opened, and we found that the wood was broken for that package. And we did that over the course of 5 days and for 5 packages, and that makes our data set. And this should answer question 3.2. And let's move on. Right, what class does our naive Bayes model predict for a new example X? So say we receive a new box and its features X is equal to mild, mild, none, which means it has a mild amount of dents, it has a mild discoloring, and it has no openings in it. And we want to know what is the class the naive Bayes model will predict for the box X given the data set. Right, so below I have a depiction of this. So here we receive our new box, and you can see it has a mild amount of dents, it's mildly discolored, and it has no openings in it. So we receive this new box with these three features. And this is going to get fed into our naive Bayes model. Right, it's going to get fed into our naive Bayes model. And we want to know what class is our naive Bayes model going to predict for this box or for this example. Right, it's going to predict that the box is going to have broken wood in it, or is going to predict that the box is going to have intact wood in it, are two classes, right? So we need to do this. We need to compute for the naive Bayes model to do this, we need to compute the probability that y is equal to broken given our condition on our example x, and the probability that y is equal to intact condition or given on our example x using Bayes theorem. Right, remember in Bayes theorem, which I've written here, right? Bayes theorem tells us how to compute conditional probability, so the probability of y conditioned on x, right? And the class for x will be the class with the highest probability, right? So we would choose the maximum out of the set of probabilities for each class. So we have the probability of y equaling broken given x, and the probability of y equaling intact given x. So whatever class, broken or intact, has the highest probability, that is the class our naive Bayes model is going to predict for this example x. Right, and with that, let's move on. So what class does our naive Bayes model predict for a new example x continued? So x is a multi-feature example, right? It has the feature dense, it has the feature discolor, it has the feature open. So it has three features, and so it's a multi-feature example. So to compute the conditional probability of y given x, we'll need to make an assumption and an observation about the features and the classes so we can use Bayes theorem. All right, so observation 1 is that the probability of x is the same for all classes y, right? Because x is the same regardless of your class y, because you're going to have the same features. Right, so the probability of x can be ignored in Bayes theorem since we only care about the maximum, right? And probability of x is the same for each class y. So we can ignore this probability of x, right? We're computing the probability of y given x, and just use the probability of x given y times the probability of y, since these are the only two terms that differ for each class. Right? I hope that makes sense. And assumption 1 is that we assume all the features are independent of one another, right? That is, one feature does not depend on another, like one random variable does not depend on one another, right? And this means that the probability of x1 and x2 and x3, given we observed class y, is going to be equal to the probability of observing x1, given we observed class y, times the probability of observing x2, given we observe class y, times the probability of observing x3, given class y. Right? And that's what that assumption means. And now, now given this observation and this assumption, now we want to find the maximum probability out of all the classes, right? Class y1, class y2, and class ym. We want to find the class with the highest probability. We just need to compute the product of the probability of observing class y times the probability of observing feature x1 given y times the probability of observing feature x2 given y times the probability of observing feature xn given y, right? And we just need to compute that product because these are the non-constant terms for each class. Right, I hope that makes sense, and we'll do an example on the next slide. Let's move on. Alright, so what class does our naive Bayes model predict for a new example x continued as 2? So the probability, say we want to compute the probability of the class or y equaling intact given our example, right? X is equal to mild discoloring, mild dense, mild discoloring, and mild openings, right? So we want to compute this probability, right? To do that, we need to compute the probability of X equaling mild, mild, none, conditioned on Y, or given Y is equal to intact, times the probability of Y equaling intact, right? And this is going to equal the probability of dense equaling mild, and and discolor equaling mild, and open equaling none, given Y is equal to intact, times the probability of Y equaling intact, right? And this is going to equal, because of our features being independent of one another, this is going to equal the probability of dense equaling mild, given Y is equal to intact, times the probability of discolor equaling mild, given Y is equal to intact, times the probability open equaling none, given Y is equal to intact, times the probability of Y equaling intact, right? So to compute the probability of Y given X, given our example X, we need to compute these 4 terms, right? And we compute these 4 terms, or these 4 probabilities, using the data set, right? So let's go through that. So the probability of Y equaling intact, right? Well, there's 3 examples of Y is equal to intact: example 1, example 3, and example 5, right? And there's 5 examples, so there's a 3/5 probability of Y equaling intact, right? And the probability of dense equaling mild, given Y is equal to intact, right? There's only one example where the dense is equal to mild and Y is equal to intact, and that's equal to example 1, right? And there's 3 examples where Y is equal to intact, right? Example 1, example 3, and example 5. So we have a 1/3 probability of dense equaling mild given Y is equal to intact. And now the probability of discolor equaling mild given Y is equal to intact is that's going to be equal to 1/3, because there's only one example where discolor is equal to mild and Y is equal to intact. And that's equal to example 3, right here, discolor is mild and class is equal to intact. And then there's 3 examples where Y is equal to intact again. So there's a 1/3 probability of discolor equaling mild and Y equaling intact. And now the probability of open equaling none, given Y is equal to intact. Well, for each example where Y is equal to intact, open is equal to none, right? For example 1, it's none. For example 3, it's none. And for example 5, it's none. So the probability of open equaling none, given Y is equal to intact, that's just equal to 3 out of 3, or 1. Or what has a 100% probability of open being none, given Y is equal to intact. And now we computed our 4 terms, 1, 2, 3, 4. And now we can compute the probability of Y equaling intact, given our example X. And so this is going to equal 3/5, the probability of Y equaling intact, times 1/3, the probability of dense equaling mild, given Y is equal to intact, times 1/3, which is the probability of discolor equaling mild, given Y is equal to intact, times 1, which is the probability of open equaling none, given Y is equal to intact. And that's equal to 1/16, or 0.067. Right, so now we've successfully computed the probability of Y equaling intact for our example, or for our box that we received. All right, and let's move on. All right, so what class does our naive Bayes model predict for a new example X continued part 3? So I'm going to leave it as an exercise to compute the probability of the other class, the probability of Y equaling broken, given our X, or given our example. And you should compute that the probability of Y equaling broken given X is equal to 1/20. And you can just go back 10 seconds and use the data set to compute that. And so what we have the probability of Y equaling broken given our example X is equal to 1/20. And the probability of Y equaling intact given our example X is equal to 1/16. Right, so this is the probability for each of our 2 classes. And since the probability of Y equaling intact, or a class equaling intact, given our example X is greater than the probability of Y equaling broken given X, since that's greater, then therefore example X has to be classified as intact. Right, so when our naive Bayes model takes in our new example, which had a mild amount of dense, a mild discoloring, and no openings, our naive Bayes model, when it takes that in, it's going to predict that that example is going to have intact wood, or that box with those particular features is going to have intact wood in it. And that should answer question 3.3. Naive Bayes model issue of a feature not present in the dataset. So recall our three features, dense, discolor, and opened, right? Take on one of three values, either none, mild, or full. However, if you look in the data set, you'll notice that the feature opened is never equal to mild. It's not in any example in our data set. So if you look at the feature opened, right, for example 1 it's none, example 2 it's full, example 3 it's none, example 4 it's none, and example 5 it's none. Opened is never equal to mild for any example. Now, this can be an issue for the naive Bayes model, right? And why is it an issue? It's an issue if a new example, x, is equal to full, mild, meaning full dense, full discolor, and mild opened, right? And why is this an issue? Well, it's because when we compute the probability of a class y given our example x, right, that's equal to the probability of y times the probability of dense equaling full given y times the probability of discolor equaling full given y times the probability of open equaling mild given y, right? So we're multiplying with the probability of open equaling mild given y. But since the number of examples where open is equal to mild is 0, right, because there's none in the data set, this probability here is going to be 0. And since we have a product of all these terms and we're multiplying by this term here, right, the probability of open equaling mild given y, right, or this makes since this term is 0, this makes the entire probability of y given x equal to 0. And not only that, this makes the probability of y given x equal to 0 for any example with the open feature equal to mild, regardless of what the other features are, right? So here, and for this example here, where x is equal to full dense, right, a box that's fully dented, a box that's fully discolored, and that's mildly opened, right, it's going to assign the same probability 0, right? It's going to assign the same probability 0 for the intact class and for the broken class, even though that you would expect a fully dented, fully discolored, and mildly open box to be part of the broken class, more likely to be a part of the broken class or have broken wood in it, right? And so this is an issue that occurs because a feature is not present in the data set. And this should answer question 4.1. Now, how do we fix the not present feature issue of the naive Bayes model? So say we make a histogram of all the times a given feature, dense, discolor, or opened, is equal to none, mild, or full for the data set. And this is shown below. So here we have a histogram of the dense feature, and this is all the number of times that dense is equal to none, dense is equal to mild, and dense is equal to full. So here you see dense is equal to 1, well, none 5 times, and dense is equal to mild 2 times, and dense is equal to full 2 times, right? Now, the issue is that for open equal to mild in the histogram, right, the histogram value for that is 0. And if it were not 0, this issue with the feature not being present would be fixed, right? So if you come over here to the opened the histogram for the opened feature, right, you can see that the histogram value for open equal to mild is 0, and that's what's causing our issue. It's what's causing the probability of y given x to equal 0 for any example that has open equal to mild, right? So we need to somehow make this not 0. And how do we do this? Well, let's move on. So how do we fix the not present feature issue of the naive Bayes model continued? So to fix the issue, we add a constant m for each class to each histogram value, right? So we come down here, right, we've edited our histogram so that for every feature value, right, we add a example of y equaling intact, represented by the green box, and we add an example of y equaling broken, represented by the blue box. So where dense is equal to none, right, the previous value was just 1, right, but since we're going to add 2 values, well, since we're going to add a m, which is 1 in this case, for each class, right, now the number of times dense is equal to none is 1 the previous time, plus 1 from the adding of m for y equal to intact, and plus 1 from adding m for y equal to broken, right? And what this does is this makes the probability of opened equaling mild given y not equal to 0, and this fixes the issue, right? So if we come down to the open histogram, right? Now, since we're adding an example for y equal to intact while open is equal to mild, right, represented by this green box here, and we're adding an example where y is equal to broken, while open is equal to mild, represented by the blue box here. Now the number of times open is equal to mild and y is equal to intact, and the number of times open is equal to, y is equal to broken and open is equal to mild is not 0, right? And this, you might think adding m might change the probability of y equal to intact given x and the probability of y equaling broken given x, and it might change how our naive Bayes model works and not work. But since we're adding m to all feature values, right, we added for dense equal to none, dense equal to mild, dense equal to full, and this color equal to none, this color equal to mild, this color equal to full, and open equal to none, and open equal to mild, and open equal to full. Since we added for every feature, right, this does not increase one probability more than the other, right? So the maximum of the probabilities of y given x, or y equal to intact given x, and the probability of y equal to broken given x is the same after we added m than as it was before we added m. And this should answer question 4.2. All right, let's move on. So fixing the feature not present issue for a specific example. So once we add m to each feature value for each class, right, as we showed in the histogram earlier, the calculation for the probability of x given y and the probability of y changes, right, because we're adding m, right, and that changes the number of examples for each feature and the number of examples of each class, right? So the probability of x given y, right, was previously equal to the number of examples of y and x, where you have an example of y and x, divided by the number of examples where you had the class 1, right? And these two terms change in the calculation after we add m to each feature value for each class, right? So what happens is that the number of examples of y and x, right, changes to the number of examples of y and x plus m, right? Because we add m to a particular for a particular class for each feature value, right? And the number of examples where we had class y changes to the number of examples where we had class y previously, plus m times the number of feature values, right? Because each feature value, right, adds an example of class y, and we add m examples, so we have m times the number of feature values is the number of examples that is the additional number of examples where we have class y, right? And so now the new probability of x given y is equal to number of examples of y and x from the previous data set plus m divided by the number of examples of y from the previous data set plus m times the number of feature values, right? And let's do a concrete example. So let's say we want to recompute the probability of the feature open equaling mild given the class y is equal to intact, right? So remember previously in the data set, the number of examples where y was equal to intact is 3, right? And the number of examples where we had open equal to mild and y equal to intact is equal to 0, right? And that was what was causing the issue. And here we have m is equal to 1, so we're adding only one example for each class to each feature value, right? And so m times the number of feature values, right? Number of feature values is we have 3 features, right? Discolored, dense, and opened, right? Each of those can take on 3 values, none, mild, or full. So we have 3 times 3 number of feature values, so we have 9 feature values. So we have 1 times m is equal to m times the number of feature values, which is equal to 9, right? And we have so now we have our our terms, we can compute the probability of new probability of opened equal to mild given y equal to intact after we added im to each feature value for each class, right? And this is going to be equal to 0, the number of examples where we have x and y, plus 1, which is m, right? Plus m, which is 1, divided by 3, the number of examples of y, plus 9, which is m times the number of feature values, and that's equal to 1 divided by 12, right? And so this is the new probability of open equal to mild given y is equal to intact, and you can see it's non-zero now, and that fixes our issue. And that's an example of recomputing the probability of x given y after we added m, right, for each feature value for each class. And this should answer question 4.3. All right, that's the end of the video of the naive Bayes model, part 2. I hope I answered the 2 questions, explained the naive Bayes model through a specific example. And the other question, what happens when a feature is not present in a dataset for a naive Bayes model? If I haven't answered these 2 questions, let me know in the comments section below, and I'll see you in the next video.